Hello, my name is Manuela Badia and I will present you today a conceptual approach of standing waves. First of all, I would like to tell you about the concept of wave, which is an oscillation who travels in time and space. What do you mean? That you can very easily measure the time of the traveling of that wave, and you can measure the length of the trajectory. Starting from this, we can define the standing waves or stationary waves, which represent an interference between two waves, a direct or so-called progressive wave and an indirect or progressive wave. And these waves are so-called waves which do not transmit matter. It's like when you throw in a ball in a lake, in the middle of the lake, around the ball forms the standing waves. Even if you throw a rock after the ball, you cannot bring the ball to you. What is important, that is very important to understand, that they appear in a confined space, like piano strings, guitar strings, or organ tubes. They travel in both directions, progressive and regressive, and at the fixed end they suffer a phase shift of 180 degrees. What does it mean? This means when I will ask you to imagine a swimmer. Okay, when a swimmer goes from one side of the pool and reach the other side of the pool, he will return, and when he will return, he will turn under the water and he will make a loop under the water, and then he will go to the surface. This is the phase shift. The phase shift is mean when he turned this 180 degrees. The progressive and regressive wave are combined by superposition, and along this stretched wire appear some loops. These loops are related to the frequency of put on the frequency generator. We can describe the motion taking account what is formed on the wire. For example, on the wire we can define points of maximum amplitude called antinodes and points with minimum amplitude called nodes. These nodes are very important because in this node, theoretically, we consider the motion is zero. The amplitude and the kinetic energy are related here, and because the amplitude is zero, no kinetic energy, so no motion. So this is the reason why you can determine with a high precision where is both on the ocean, if he or a person in the ocean, if he or she doesn't have pedals or they are not oceanic currents or wind, because they move only in the region where we have amplitude. The number of antinodes will describe the wave, the standing waves. If we have a certain frequency called fundamental, we will see here we have only one antinode. If we multiply the number of the fundamental frequency with an integer number, we can obtain second harmonic, third, fourth harmonic, and so on. This is all called vibrational spectrum of the standing waves. What is very important here, I will show you an experiment.
This number, so 8.5. Here we go.
This is a wave in a very slow motion measured with a camera. And now, if you can see, we can double the...
It's basically the scenario of a jump. Now, I can find all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess, what is that, around 25.5?
As a review, I will as you can see, the standing waves. And I would like to review the theory I will present to you, that the standing waves are obtained by superposition between a progressive and regressive wave. They do not transmit matter due to the zero amplitude in nodes, and the superior harmonic are simply and easily obtained by multiplication of the fundamental with an integer number. And I will give you a quiz here, and I will thank you and see you next time.